Hello. In this video, I want to give you a short introduction to the ways in which we can use R to calculate summary statistics for a dataset. Throughout the video, we're going to be working on this particular dataset. Thus, before we start, I want you to pause the video and think about what you might do to analyze this data if you were given pen and paper and not a computer. Okay, so let's start analyzing this data with R. The first step we are going to take is that we're going to load this data into an R-style list using the commands that you've learned earlier in the semester. We can then do some of the analyses you hopefully came up with when we paused the video. For example, we can calculate how many pieces of data that we have by using the length command as shown here. R tells us that there are 100 data points here. We can also use R to calculate the mean. By hand, we would have to do this using the formula showed on the slide, which would mean adding our 100 numbers together. With R, you can see that it is one line of computer code. We might also choose to calculate the standard deviation. As you can see from the formula here, doing this by hand is even more of a pain in the arse than doing the mean by hand. It is thus good to know that we can do it with one line of R. Typically, when I ask students for suggestions as to what to do with a dataset, calculating the mean and standard deviation is what they come up with. It may surprise you to know that these are rather sophisticated mathematical ideas. There are considerably simpler things we might try that students usually never think of. For example, we can make a graph of the data as shown here. I create a plot in R using the plot command that is shown here. I pass to this command a list of x coordinates and a list of y coordinates for the points I want to plot. Furthermore, and rather pleasingly, R labels the axes of my graphs using the variable names that I plotted on the x and y axis. In the graph that I have shown here, the y coordinates of the plotted points are the values of the data points in my sample. The x-axis is then a numerical index that tells me something about the order of the points in my sample. I created this x data using the seq command in a way that ensures that the x-coordinate of the first point is 1, the x-coordinate of the fourth point is 4, the x-coordinate of the 8th point in the sample is 8, and so on. Now that we have the data plotted, let's digress briefly and talk about how we should interpret the mean and standard deviation that we calculated on the previous slide. If you remember from that last slide, the mean was 2.74, which lies about here. You can see that the mean is roughly in the middle of all of these data points. The standard deviation was about 1.21. If we draw a box around the mean with a side length of a standard deviation, as shown here, this should encompass about 66% of our data points. By plotting our data in this simple way, we can thus see if the distribution of points accords with our expectations based on calculating the mean and standard deviations. Sometimes data doesn't follow this simple pattern because, as you will learn in SOR 1020 and other modules, when we assume that summary statistics offer meaningful information about a distribution, we are making some pretty significant assumptions. Plotting the data as we have just done is fine, but there are other, more compact representations we can generate. For example, I am certain that you will have encountered the process of calculating a histogram at some point during your education. As you hopefully know, to calculate a histogram, you need to calculate how often each of the possible outcomes occurs in the data sets. In other words, we calculate the number of times n that our random variable capital X is equal to a particular value small x. For example, Suppose that we wanted to calculate how many 6s there are in this dataset. We can run through the entire dataset as shown here, and if the value is a 6, then we add 1 to the count n. By doing this, we can determine that there is exactly 1 6 in this dataset. Doing this by hand is very boring, so let's get R to do it for us. To do this, we use the table command as shown here. Furthermore, when we output the freq variable that this command gives us, you can see that we get a nice table that shows us that there is 1 0 in the dataset, 16 1s, 27 2s, 27 3s, 23 4s, 5 5s, and 1 6. We can even plot freq to get a nice graph as shown here. Lastly, much as we did on the last slide, we can superimpose the values of the mean and standard deviation on this graph and see how much of the data set lies within one standard deviation of the mean. I think the simplest thing that we can do to the data is to sort it into ascending order. To do this with R, we use the command sort as shown here. When the resulting list of numbers is output, you can see that the sequence of numbers now increases monotonically. Better still, if we now plot the sorted data with the sorted data on the x-axis and a numerical index on the y-axis as shown here, we get a stacked plot like the one shown here. This is an alternative way of viewing the histogram that I discussed on the previous slide. You can get the same idea of sorting the data to generate an estimate of the cumulative distribution for the data. You spent a lot of time learning about cumulative distributions in SOR 1021, so being able to generate estimates of these distributions from datasets is rather useful. In fact, this is so useful that R provides you with an eCDF command that allows you to calculate and plot the cumulative probability distribution without first sorting the data as shown here. The cumulative distribution is useful as it allows you to make statements such as 50% of the data is less than or equal to 2. You can make these sorts of statements by drawing a horizontal line at 0.5 as shown here. You can then see that all the data points below this line are 3 or less by reading the x-axis. By moving the vertical line up or down, you can determine that 20% of the data points are less than or equal to 2, and that 80% of the data points are less than or equal to 4. These quantities that we're calculating are called percentiles, and again, R makes it easy to calculate these percentiles from the dataset by providing you with a function that does it for you. In this case, the function is called quantile as shown here. You pass to this function the data and then a second argument that gives you the percentile that you want to compute. As you can see here, this second argument can even be a list. If it is a list, R will calculate all the percentiles you require and show you the result in a nice table, as you can see here. So let's summarize by reminding ourselves that we started this video by challenging ourselves to find out something about this dataset. During the video, I have shown you how we can use R to calculate the mean and variance of the dataset. I have also shown you how you can use R to calculate histograms so that we can make statements such as 27 of the data points are equal to 2. Last of all, I have shown you how we can sort the data and compute the cumulative distribution function. We can thus make statements such as 20% of the numbers in the sample are less than or equal to 2. Before we finish, I want you to note that all these analyses reduce the amount of data that we had. In other words, if we are only given the results from the analyses that I've introduced in this video, we know less than we would do if we were given all the data. But that is kind of the point. In statistics, we collect data by doing experiments, and then we calculate means, histograms, or sort the data from those experiments. In parallel to this activity, I can construct mathematical models of idealized datasets using probability theory and do the same operations of means, histograms, and sorting these idealized datasets. I can then hopefully make some connection between the results from my experiments and the idealized models that I have developed. The point I want to finish with is that whenever we analyze data, we have to make assumptions about the processes that developed the data. In other words, we have to introduce a model. Data does not provide self-evident answers to our questions about the way the world operates. Whenever we analyze the results of an experiment, we must impose our view on how the world operates in our analysis. This is important to remember, as we are all fallible, and the assumptions we make about the universe and the resulting conclusions we come to when we analyze the data that we have about the world from experiments are often wrong.